I'd like to finish talking about integration by parts by looking at three topics. Firstly, I want to look at some common integrals that we haven't been able to do up to this point. I want to look at situations where you have to do repeated integration by parts, and that will lead into what's called the tabular method, which will allow us to do certain integrals very quickly. Firstly, I'd like to look at the integral of the natural log of x with respect to x. Thinking, as we have been thinking, of these things as being multiplied together, we don't have a great deal of wiggle room here. We have the factor natural log of x and also dx. If I were to take the dv to be natural log x dx, my problem to do integration by parts would be equivalent to the problem I started with, and I don't know how to do that. So I have to do something else. I'll let the u equal natural log of x, and I'll let the dv equal dx. This means that the derivative of u is 1 over x. As a result, du is 1 over x dx. Meanwhile, since dv equals dx, pretending these things are fractions, the derivative of v with respect to x is 1, v is an antiderivative of 1, v equal x is an antiderivative. So in the integration by parts formula, the integral of u dv is u times v minus integral of v du. If you write all those quantities down, you get x multiplied by natural log x minus the integral of v du is x times 1 over x dx. In this integral, the x's in the integrand actually cancel out, and you're just trying to find an antiderivative of 1. The integral of natural log x with respect to x is x times natural log x minus x, and then plus a constant to get all possible antiderivatives. As a sanity check, you can take the derivative of your answer and make sure that you get what you're supposed to, which in this case will be natural log x. I'll have to use the product rule on this first piece because it's x multiplied by natural log x. The derivative of x with respect to x is 1, and the derivative of a constant is 0. X times 1 over x is 1, so this turns into 1 plus natural log of x minus 1. The 1's cancel out, and I find out that our answer is right. The integral of natural log x dx is x times natural log x minus x plus a constant. As a minor variation on a theme, think of the integral of x squared plus 5x plus 1 times natural log x. X squared plus 5x plus 1 is a polynomial. If you either differentiate that or integrate it, you get a polynomial. So I'm looking for something that when I differentiate it will bring me a great simplification. I ought to make u equal natural log of x. Derivative of u with respect to x is 1 over x. du is 1 over x dx. dv has to be all of the other factors in the integral. dv dx must be x squared plus 5x plus 1. V is an antiderivative of this, so it's easy to calculate. 1/3 x cubed plus 5/2 x squared plus x. As always, we'll wait till the very end to put the constant of integration on. If you then write down the integration by parts formula, there's no calculus left to do in this bit. And in this bit, I've got a polynomial and I've got a factor of 1 over x. That'll just lower the power on each one of those terms. The result is a polynomial, which is easy to integrate. So the integral that I'm trying to calculate is given by this quantity. If I want to find an antiderivative for the arcsine of x function, I'm in the same position that I was when I was looking at natural logarithm of x. The only way I'm going to get any place in this problem is if I let u equal arcsine x and dv equal dx. This is the only chance that integration by parts might help me out here. Derivative of u with respect to x, the derivative of the arcsine function is 1 over square root 1 minus x squared. Du is that quantity times dx. Derivative of v with respect to x is 1. V equals x is an antiderivative. So the antiderivative for arcsine x is going to be x times arcsine x minus the integral of x times 1 over radical 1 minus x squared dx. This is not on our list of integrals that we immediately know how to do, but on the other hand, it's not too bad either. There is a 1 minus x squared in the problem. The derivative of that is negative 2x. Having or not having the constant factor can be dealt with. The thing that's important to notice is I have a factor of x here. So we'll do this last integral by doing a substitution. Usually when we do a substitution, the variable of substitution is called u. I don't want to use that letter because it'll get me confused with integration by parts. So I'm going to let p equal 1 minus x squared. dp dx is negative 2x. dp is negative 2 times x times dx. And since what I actually have in my integral is x multiplied by dx, I'll rearrange that until it says x times dx is negative 1/2 times dp. If you write everything in the integral in terms of these quantities p, x dx, that factor times the last one, becomes a factor of negative 1/2 times dp. The rest of it, 1 over square root 1 minus x squared, is 1 over square root of p. The square root of p is p to the 1/2 power. 1 over the power of some variable is that variable to the negative power. So 1 over square root of p is actually p raised to the negative 1/2 power with respect to p. We have a technique for this. We increase the power by 1, and we have a factor that is the reciprocal of the new power as a factor in front. So the integral of secant cubed x dx is secant x tangent x minus integral tangent x secant x tangent x dx. The integral that remains at the end is to find an antiderivative of tangent squared secant x dx, which unfortunately is not on our list of things we know. We do have a trig identity though. tangent squared of x is secant squared of x minus 1. If I replace the tangent squared with this expression, we find out that the integral secant cubed x dx is secant x tangent x minus the integral secant cubed x minus, inside the integral, secant x dx. If you split that up into two pieces, the integral of secant cubed of x with respect to x is secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. This is kind of bizarre. On the one hand, there is some good news. The integral of secant x dx is on our list of things we know how to do. Weirdly, though, the thing that I'm trying to calculate has shown up in this formula over here. So it looks like we're going around in circles, but we're not. What I can do is I can add the integral of secant cubed x dx to both sides. That'll make this term go away. And over here, I'll have twice integral secant cubed x dx. Divide through by 2, and you'll find out that the integral of secant cubed x dx is 1/2 times the quantity secant x tangent x plus natural log absolute value secant x plus tangent x, that's this integral, plus a constant. In a similar way, if I have an exponential function of type e to the ax, where a is a constant, and a trig function that's either sine or cosine of bx, where b is a constant, we can work out the integral of the product of such things. In this integral, I'm going to let the u be e to the 2x. The derivative of u with respect to x is the derivative of the exponential, which is the exponential, evaluated at the same place the original was, and then multiplied by the derivative of 2x, which is 2. So du dx is 2e to the 2x, du is 2e to the 2x dx. On the other hand, dv has to be the rest of the factors. The derivative of v with respect to x must be cosine of 3x. V must be an antiderivative of cosine 3x. Sine of 3x would almost get the job done, but it would have an extra factor of 3, so the v should be 1/3 sine of 3x. If you write out the integration by parts formula, you find out that the thing that we're interested in is 1/3 e to the 2x sine 3x minus the integral of 2/3 e to the 2x sine 3x with respect to x. This is not very encouraging because I started off with an integral that had exponentials and trig functions in it, and to finish it, I have to do the same kind of integral. It's got exponentials and trig functions in it. It turns out, though, if I do my integration by parts a second time, I can get around that. So to do that last integral, having pulled the factor of 2/3 out front, I'm going to let u equal e to the 2x. du, as before, will be 2 times e to the 2x dx. dv will be the rest of it, sine of 3x dx. The derivative of cosine is negative sine, so I'm going to need an extra negative sign to balance that out. Also, I would pick up a factor of 1/3, so v is going to be negative 1/3 cosine of 3x. So using integration by parts to get the integral that was at the end of the integral that I started off with when I did parts, I get this messy expression. But again, it looks as though we're going around endlessly in circles because now I'm back to having an integral of cosine 3x e to the 2x, and that's what I'm trying to figure out. So if you write out everything we've figured out, the integral of e to the 2x cosine 3x with respect to x is this mess. Minus minus is plus. Minus plus is minus. The thing that I'm trying to figure out shows up on the other side of the equation. Now, just as with the integral of secant cubed, this doesn't turn out to be as big a problem as you might think. To try to keep the arithmetic under control, I've multiplied through on both sides by 9. This clears all fractions. I have 9 times the integral that I want to find is some algebra trigonometric expression minus 2 times the thing that I'm going to try to find. I'm going to add 2 times integral e to the 2x cosine 3x to both sides. Over on the right, that cancels this term out. Over here, I used to have 9 times that integral. I'm going to add 2 times the integral to get 11 times it. I'll go ahead and factor the e to the 2x out. And then finally, dividing both sides by 11, I find out that the integral of e to the 2x cosine 3x is 1/11 times the quantity 3 sine 3x plus 2 cosine 3x multiplied by e to the 2x with a constant of integration added on. Lastly, there's a thing called the tabular method. If the integral that you're doing can be thought of as the integral with respect to x of the product of two things, one of which you can easily differentiate and the derivatives become simpler after a time, while the other piece you can integrate one after another, then very often you can use a trick in order to find the integral without very much work. So comment, the derivatives of x cubed plus 2x squared plus 5x plus 2. The function itself is a cubic polynomial. Its derivative is a quadratic. Its second derivative is a constant. Its third derivative is 0. And all derivatives after that will be 0 as well. Also, antiderivatives for this other factor, e to the 2x, is easy to figure out. It's 1/2 times e to the 2x. If we wanted to be picky, we would put the constant of integration on. So I'm going to do integration by parts here. Now, I'll leave the details to you to work through, but u is going to be x cubed plus 2x squared plus 5x plus 2. As a result, du is 3x squared plus 4x plus 5 dx. dv is e to the 2x dx, which leads you to v being 1/2 times e to the 2x. So if I do the integration by parts formula, I'll have u times v minus the integral of v. I've split the v up into these last three factors, 1/2 e to the 2x. du has this quadratic factor and the dx. So I'm writing it in this order for a certain particular reason. The original problem had a cubic times an exponential. To finish this, I only have to calculate a quadratic times an exponential. So we're going to do integration by parts again. In the integral that remains, I'll let u equal 3x squared plus 4x plus 5. So the du is 6x plus 4 dx. The dv will be 1/2 e to the 2x dx. When I integrate that, I'll pick up another factor of 1/2. So the v will be 1/4 times e to the 2x. Now, I'm not going to simplify any of this stuff because I've got a reason for doing that. This integral, I'm going to do it with parts. I'll let the u be 3x squared plus 4x plus 5. Du will be 6x plus 4 dx. We pick up another factor of 2, and then we can write down the integration by parts, which, continuing to write out in gory detail all of these factors, becomes this quantity. Notice that I'm going to have a negative sign here, which gets attached to this term, but then minus minus will be plus. Then finally, I have to do this integral. The integral of 6x plus 4 times 1/4 e to the 2x. We'll use parts again. This time u will be the linear polynomial, 6x plus 4. Du dx is 6. Du will be 6 times dx. V is going to be 1/4 e to the 2x dx. So v is an antiderivative of that. You pick up another factor of 1/2, and you get 1/8 e to the 2x. So the integral that we have at the very end is 6x plus 4 times 1/8 e to the 2x minus 6 times 1/8 e to the 2x dx. The integral that's at the end is this. So having done what seems like about 1,000,000 cases of integration by parts, the integral that I'm after is this cubic times 1/2 e to the 2x minus this quadratic times 1/4 e to the 2x plus this linear chunk times 1/8 e to the 2x minus 6 times 1/16 times e raised to the 2x power, and then you tack on the constant of integration. Now, a reasonable question is, why did I not simplify any of this stuff as I went along? It's because I want to be able to identify where these terms came from. So you might want to make a note of all of this stuff that we're adding and subtracting, because we're going to take the thing that acts nice with respect to differentiation and differentiate it one time after another. We are going to take the thing that's nice to integrate and not differentiate it, but integrate it one time after another. The derivative of x cubed plus 2x squared plus 5x plus 6 is 3x squared plus 4x plus 5. The derivative of that is 6x plus 4. The derivative of that is the constant 6, and all further derivatives are 0. The thing I start off with, comprising the rest of the factors in the integral, except for the dx, is e to the 2x. Integrate that, and you'll get 1/2 e to the 2x. Integrate that, and you'll get 1/4 e to the 2x, 1/8 e to the 2x, 1/16 e to the 2x, and if I wanted to write some more of those down, we could do that. It's unnecessary though. Take the quantities that are in the first column and draw a downward sloping line until you get to the next row in the second column. Do the same here, do the same here, and do the same here, And what I'm going to do is multiply the things together. So you'll have x cubed plus 2x squared plus 5x plus 6 multiplied by 1/2 e to the 2x, and that is that piece. The next piece, 3x squared plus 4x plus 5 multiplied by 1/4 e to the 2x is that piece, except because of the uv minus integral of v du, I subtract that one. The next one is 6x plus 4 times 1/8 e to the 2x, 6x plus 4 times 1/8 e to the 2x, and then because I'm doing another round of integration by parts, the next one will be subtracted 6 times 1/16 times e to the 2x, 6 times 1/16 times e to the 2x. This chart correctly produces the things that I have to add and subtract from each other. It's the product of these two things minus the product of these two things plus the product of these two things minus the product of those, and all later terms are 0 because I've run out of derivatives on the polynomial. This is called the tabular method, and if I have something simple like a polynomial times an exponential, I can basically just write the answer down. Say you wanted to integrate x cubed e to the x. The derivative of x cubed is 3x squared. The derivative of that is 6x. The derivative of that is 6, and all further derivatives are 0. In the second column, I am integrating e to the x, not differentiating it, but the integral of e to the x is e to the x all the way down. Draw your downward sloping diagonal lines. We're going to multiply together the stuff that's connected by the downward sloping lines, and we're going to alternatively add and subtract them. So I'm going to add x cubed e to the x. I'm going to subtract 3x squared e to the x. I'm going to add 6x e to the x, and then I'm going to subtract 6e to the x. All of those terms have a factor of e to the x in them, so I might as well factor it out. I claim that the antiderivative of x cubed e to the x is this function plus the constant of integration. To check that the work is correct, I'm going to take the derivative of my answer. Now, my answer is a polynomial times the exponential function, so I have to use the product rule on this. This is the original polynomial times the derivative of e to the x, which is e to the x, plus the second function, which is e to the x, times the derivative of the first function. Derivative of x cubed is 3x squared. Derivative of 3x squared is 6x. Derivative of 6x is 6, and the derivative of 6 is 0 because 6 is a constant. If you factor the e to the x out and write out what's left, the 3x squared terms cancel out, so do the 6 times x terms, and here I've got minus 6 and plus 6. The only thing that doesn't go away is x cubed times e to the x. So you see, this tabular method actually does work. This is all I'm going to say about integration by parts as such. Coming soon, more integration techniques. I hope everyone is doing all right. We'll talk again soon.